Okay, so I want to talk about interval and set notation, which are just a couple of different ways to basically represent a bunch of numbers that you have. And so I want to start with this question: what numbers, if I subtracted 3, would be greater than 1? So for example, 8, if I subtract 3, would give me 5. Is 5 greater than 1? Yeah, so 8 should be part of my solution set. Whatever I say, 8 should be part of it. Okay, so what we'll do here is we'll write an inequality to solve this. So we're going to say, what numbers, if I subtracted 3, would be greater than 1? So x something minus 3 needs to be greater than 1. And then you'll solve this using some algebra. I don't know why we're adding 4. That's dumb. Let's add 3. I'm probably writing 4 because I know I'm about to get 4 here when I add 3 to both sides. All right, x needs to be greater than 1 plus 3 is 4. Okay? So what's interesting here is, and this is not a super interesting case, but anything greater than 4, if you subtract 3 from it, would give you a result that is greater than 1. And that's not earth-shattering or groundbreaking or anything, but this, the ability to do this and to be able to talk about the solution set is really important. So there are several ways that we can talk about, hey, all the numbers that are greater than 4. So this is the first way we talk about it. We would call this just kind of an inequality. You could say it in words. You could say any number greater than 4. You could say that. We would know what you mean. Greater than 4, and I'll actually spell 4 out. Another option that we've talked about is graphing it on the number line. So if you draw a number line, that arrow's on the struggle bus a little bit. So draw a number line here, and we will highlight 4. That is a number that we are particularly interested in. And we're just going to show visually, hey, anything greater than 4 would work here. So you can just shade with an open dot there because you don't want to include 4. If you did 4 and subtracted 3, it would give you 1, which is not greater than 1. 1 is equal to 1. So that's an option. And I want to talk about 2 new options for you to use to talk about any number greater than 4. Okay, and so the first one here, which I'm labeling number 4, is interval notation. And the idea with interval notation is that I'm giving a starting number and a stopping number. So what I'm going to say here is everything greater than 4. And the way that I do that with interval notation is I'm going to say, hey, I want you to start at 4, and then I want you to end at, and I actually don't want you to ever end, so I'm going to write infinity here. This right here is interval notation. That's it. That's all you have to say right there. So you say starting at 4, going up until infinity, any number in that range or that interval would work. Okay. If it was only 4 to 30, you would put, parenthesis 4 comma 30, and then you'd put a parenthesis or a bracket. But we'll talk about the brackets here in just a sec, and when to use a bracket and when to use a parenthesis. The other notation that we've got is called set notation. This is going to seem really weird, but it is kind of helpful and useful. And set notation is where we say the set of all numbers x. That's how we read this. So we read this like the set of any number x this little guy means which is an element of or a part of, and then we're going to put a bold-faced R here, so we're just going to do an R with a little extra line on the left side of it. That's, I'm running out of room here. This guy right here stands for the real numbers. So let's pause for a second. So we're saying the set of any number x, which is an element of the real numbers, such that, that's what that little line means there. That line means such that X is greater than 4. And this is the point at which people are like, seriously? We already wrote the inequality. Why do I need to write this extra stuff here if I can just say X is greater than 4? And the reason is because sometimes we're dealing with real numbers. Sometimes we're dealing with only like whole numbers. So theoretically, 7.5 would work here. 7.5 minus 3 is greater than 1. Sometimes it doesn't make sense to have fractions of something. Like if I ask, which we're going to do here in a second, how many of these things could I buy? You wouldn't be like, well, you could purchase 7.3 of them. You would just say, well, you could buy 7 or 8, you know. And so this notation is helpful when we just want to be super clear about what all is in the solution set. Okay, so just to write this out, so without a lot of the writing with it here, we would say, little curly bracket here, X is an element of the real numbers such that X is greater than 4. So any real number greater than 4 would work here. That's set notation. This right here is interval notation. Okay, so let's look at another example here and walk through that. So this says, what if you had $80 and you saw a bunch of packs of cards at the store that were each $5, but you need $10 to eat lunch? Okay, so obviously you can spend up to $70, right? But you have to save $10 to eat lunch. The question is, how many packs could you purchase? And you could just kind of guess and check, problem solve this, but since we're on this idea of using algebra and functions, let's do that. So if you have $80, so we're going to start with $80, and every time you spend $5, you're going to buy a pack of cards. I'm going to say if you subtract 5x, where x here is equal to the number of packs of cards, 80 minus 5x would be how much money you would have left, right? So for example, if you bought 3 packs of cards, you would throw a 3 in here, and then you would do 80 minus 5 times 3, which would be 15, which means you would have 80 minus 15, which would be $65 left over. So this right here is a function which tells you how much money you have left. We need to make sure that the amount of money we have left is at least $10. So what we can do is we can just say that this function needs to be greater than or equal to 10. And so what we've done here is we've created an inequality that can model how many packs of cards we're going to buy and how much money we have, and we can figure it out and solve it from there. So let's actually go ahead and solve this. So I would, if I was solving this, I would subtract 80 from both sides. When you do that, you get negative 5x is greater than or equal to 10 minus 80 is negative 70. And then we're going to divide by negative 5 here. Please do not add 5. And when we do this, these cancel, we get x. And then, hey, don't forget, we divided by a negative number, so this sign needs to flip here. So x is going to be less than or equal to, and then negative 70 over negative 5 is 14. So this is our first way of expressing the solution here. What does x stand for? Well, I erased it, but we said earlier that x was the number of packs of cards. And so what we're saying here is that the number of packs of cards that you can buy has to be less than or equal to 14. If you buy more than 14, you're not going to have enough money left to eat lunch. So let's talk about each of our ways to do this. So we've got the inequality. We would say, so that's the first way of talking about it. Number 2 would be, in words, you could purchase, maybe we could say up to 14 packs. 3 would be to visually demonstrate on a number line how many packs of cards you could buy. So I'm going to put 14 here, and theoretically you would want to stop at 0 because you can't really purchase negative packs of cards. So I'm not just going to shade left forever. What I'm going to actually do is say I could purchase 14. I could purchase exactly 14. I could also purchase exactly 0 if I wanted to. So we'll put a shaded in dot there. And really any number of packs in between 0 and 14, like 1, 2, 3, 4, 5, 6, 7, you could go all the way up to 14. But any number between 0 and 14, any whole number you could purchase. I don't think if you walked up and said, hey, can I purchase 0.6 packs of cards, the guy would be like, oh, sure, let me pull out 40% of the cards in this pack and sell it to you at 60% of the price. That would be dumb. Nobody would do that. Now some of you are going to challenge me and go to the mall and get somebody to do that for you. Okay, so that's the number line. Let's talk about interval notation. So we're just trying to provide an interval that would satisfy the constraint here that you have to be less than or equal to 14. I'm also going to say you need to be greater than or equal to 0, right? Because you can't buy negative packs. So what we're going to do is we're going to say you could theoretically purchase 0. You could also go all the way up to 14, and you could purchase 14. You'll notice here that I've done brackets, okay? So we're going to leave a little note here for you. Use brackets instead of parentheses if you want to include the number. If we wanted to go up to 14 but not actually say that you could purchase 14, you'd put a parenthesis there and you'd say, hey, so you can do 0, including 0, up to 14, but you can't actually buy exactly 14. So maybe it would be better to say 13 with a bracket there instead of 14 with a parenthesis. It just depends on the context, okay? So we will use parentheses. So use parentheses if you don't want to include the end number. Okay, so that is interval notation. And then now we're going to talk about set notation. So this was interval notation. Set notation, in this case, we're going to start with the typical curly bracket here. And we're going to say X is an element of, okay, and this is going to get a little confusing, but bear with me. I'm going to say as long as X is an element of the whole numbers, and I don't like the way I drew that. That's about the same. Such that X is greater than or equal to 0 and at the same time less than or equal to 14. And I don't like my curly bracket there. I'm not very good at these curly brackets. There we go. That's a little better. So this would be set notation. So a lot of people are like, what the heck is this? So right now we need to talk about different kinds of numbers. So we have types of numbers, okay? The first type of number, which is kind of the most basic, are, so types of numbers. Are whole numbers. And we use this symbol with like an extra line on the left there on the W. These are the whole numbers. This might sound weird, but there's actually not 100% agreement on the types of numbers, but this is the most conventional that I've seen. So the whole numbers are all of the numbers that don't have a fraction in them that are just whole. So like, and we start at 0. So it's 0, 1, 2, 3, 4, 5, on and on forever, up to infinity. Okay, those are the whole numbers. The natural numbers are the exact same as the whole numbers, except the natural numbers are what we call the counting numbers, is probably what you'll hear them referred to as the most. And it's the exact same except for 0. We take 0 out. So the natural numbers and the whole numbers are the exact same, except the natural numbers don't include 0. So 1, 2, 3, 4, 5, 6, on and on forever. Those are the natural numbers. The next set we have, and let's actually switch the order on these. So technically the natural numbers should be above the whole numbers. I will do that after I finish with the notes here. The next set of numbers is called the integers, which is a bold-faced Z. Looks like that. And the integers are all of the whole numbers, but also all of the negative whole numbers. So we'll go back to negative infinity and then pick up at like -3, -2, -1, 0, 1, 2, 3, so on and so forth. So the integers are basically just whole numbers, but they also include the negatives as well. Next thing we want to talk about is the rational numbers, which is a bold-faced Q. This is the rational numbers. This is anything that can be expressed as a fraction or a decimal. So this includes all fractions of integers, I should say, where you have integer numbers in the fraction on the top and bottom. All fractions, decimals, including repeating decimals. It's actually kind of complicated to explain exactly what the rational numbers are, what's included in the rational numbers, but just a basic explanation will do for now. Then we've got the real numbers. And this is any number that falls into one of these 4 categories. So it's essentially any number you can think of, with the exception of the imaginary numbers. All right, then the next and the last one I want to talk about is the complex numbers. So complex numbers. These numbers have a real part and an imaginary part. So they'll have like 4 plus 3i, where I is the imaginary number, which we will get into later this year. Okay, the reason this is important is if we're specifying a solution set, and we don't want people to think, oh yeah, sure, you can buy a part of a pack of cards. No, you have to buy a full pack of cards. You can't buy 5.2 packs. You can either buy 5 or 6. It's really important to specify, if that's the case, that we're only dealing with whole numbers here. Like, we're not dealing with rational numbers where you can buy part of something. Okay, so that's just a really important distinction to make, and I want to make sure we talked about those types of numbers. So to conclude then, what we're saying is, I zoomed out here, you can purchase any whole number of cards as long as that amount is between 0 and 14, including 0 and including 14. So you could buy 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, or 14. It might not seem like a big deal that we write it like this because I just literally said the solution set out loud, but imagine a solution set that had like 5,000 numbers in it, but it was only whole numbers. Sometimes it's just a little easier to use the set notation to represent that set. Okay, so last thing I want to talk about here is compound inequalities, and this is inequalities. Here's our first example for you, where you've got 2 inequalities going on at the same time. So what if we had something like 2 is less than or equal to 2x minus 4, which is less than 8? And we were supposed to solve this, graph it, give the answer an interval and set notation, yada, 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 all that fun stuff. You get a couple options here. You can break this apart into 2 separate inequalities and solve them individually and then merge them at the end. So like you could come over here and do 2 is less than or equal to 2x minus 4. That would be your first inequality. Your second inequality would be 2x minus 4 is less than 8. So your first inequality would be this part right here. Your second inequality would be that part right there. You can do that if you'd like. That would totally work. If you did that, I mean, you'd get what? 2x is less than or equal to 6, and then x greater than or equal to 3. Over here, you'd get 2x is less than 12, x is less than 6. So you'd be saying is, hey, at the same time, x needs to be greater than or equal to 3, and it also needs to be less than 6. You can do that. Excuse me. I like to take a little bit of a shortcut, and that is to actually solve both inequalities at the same time. So what we're going to do is we're going to add 4 to both sides, because that's how we would solve if we had this 2x minus 4 part here by itself. What's weird about this is that we're going to do it on all 3 sides. So we're going to do it over here, and we're going to do it over here, because if we do it on one side of the inequality, we have to do it on the other side, and we also have to do it on this other side as well. So once we've done that, we simplify. We've got x less than or equal to 2x. The 4 and the minus 4 get rid of each other. This is less than 8 plus 4 is 12. And now we just keep going, except instead of just dividing by 2 on 2 sides, we have to do it on all 3 sides. Again, the goal is just to get x by itself. So, all right, 6 divided by 2 is 3. Is less than or equal to 2x over 2 is just x. And then that's less than 6. And hey, look at this. So this was the exact same answer we got before with a little bit less writing. So that's nice. So now we need to talk about this. So how would we graph this like on a number line? So if x needs to be greater than or equal to 3 and less than 6 at the exact same time, what we'll do is we'll draw our number line. And we will put down 3 and 6. Those are the numbers that I particularly care about. We're going to shade in the 3 because it's less than or equal to. And then we will leave an open dot for the 6 because it's just less than. And now we have to ask ourselves, okay, what are all the numbers that are both greater than or equal to 3 and less than 6 at the same time? So for example, would 4 work as a number? Is 4 greater than or equal to 3 and less than 6 at the same time? Yes. So 4 should be shaded. Is 7, would 7 work? Is 7 greater than or equal to 3? Yes. And less than 6? No. 7 should not be shaded in once we're done with this. So the question is, what part should be shaded here? And I'm going to say that it should be everything in between 3 and 6. The green area is good. The red area is bad. What's wrong with the red area here? The red area here is not less than 6. Okay. What's wrong with the blue area here that I'm shading in? The problem with the blue area is that it's not greater than or equal to 3. Okay. So we need to satisfy both of these conditions at the same time. The only zone up here that does that is this green zone right in between. So what we're going to do to answer this is we're just going to draw a line here in between there. So that would be our solution if we were going to graph it on the number line. What if I had asked you for interval notation? Okay, so the interval notation solution on this, interval notation solution would be, we are going to go from 3, we are going to include 3. That's why we put this bracket here instead of a parenthesis. And then we are going to go to 6, but we're not including 6, so we're going to put a parenthesis there. So this right here, that is interval notation. That's your solution. How about set notation? So set notation, the solution in set notation would be the set of all numbers x in the real numbers such that, let's see, x needs to be greater than or equal to 3, and it also needs to be less than 6. That would be your answer in set notation. Okay, so that's how you would do a relatively simple compound inequality. But wait, there's more. So I want to show you another example here. And on this one, we're just gonna do it relatively simple. I'm just gonna write x is greater than or equal to 4 and x is greater than or equal to 6. So now they're basically already solved. We don't really need to solve them. But now the question is, if we graph this, what would the solution set look like? So here's 4, here's 6, and now I'm looking for all possible numbers that fit both of these. So they have to be true for both of these. We need our number to be greater than or equal to 4 and at the same time greater than or equal to 6. So if you get a little confused on these, sometimes what I'll do is I'll just go along and I'll plot numbers. Like, would a number right here work? I don't know, what is that, 3, maybe 3.5? Would a number right there work? Is 3.5 greater than 4 and greater than or equal to 4 and greater than or equal to 6? No, it fails that one and it fails that one. So that blue X there should not be shaded in. How about something like right here? What if we wanted to look at like 5? Okay, so is 5 greater than or equal to 4? Yes. Is 5 greater than or equal to 6? No. So it passes the first one, but it fails the second one. It's got to pass both of them for us to draw it. So 5 should not be in our solution set. How about something over here? So would something like 7 work? Is 7 greater than or equal to 4? Yes. Is 7 greater than or equal to 6? Yes. Okay, so 7 should be shaded in. So what we'll do here is essentially, if we're looking for all numbers that are greater than or equal to 4 and greater than or equal to 6, really the only thing that matters here is that they're greater than or equal to 6. So what we'll do here is we will shade and say, hey, you know what? Anything greater than or equal to 6 would technically fit this bill, and it would be true. Okay? How do we do that for interval notation? We would say including 6, so put a bracket, all the way up until we get to infinity. Always put a parenthesis for infinity. That right there is interval notation. How about set notation here? So the set all values of x in the real numbers such that x is, you can just say x greater than or equal to 6. That will be your set notation answer. Let's get another example here. So we're just going to look at different combinations of these compound inequalities and the kinds of solutions that they produce. What if we had something like this? How about 23 is less than 3x plus 2, which is less than 14. Okay, so again, you're more than welcome to break these up if you want. I'm just going to solve them all at the same time. So I'm going to subtract 2. My goal is to get this x by itself, so I'm going to subtract 2 to get rid of that 2. When we do that, we're left with 21 is less than 3x. The 2's go away. 14 minus 2 is 12. And then from here, I'm going to divide by 3, divide by 3, divide by 3. So what are we left with? 21 over 3 is 7. 3 over 3, those go away. We're just left with x here. And then 12 over 3 is 4. Okay, and so now what we've got is we have, at the same time, we need x to be, and careful the way you read these. I know most people think of this as a less than symbol, but what this is saying is that 7 is less than x, which is also the same thing as saying that x is greater than 7, right? If you read it this way, x is greater than 7. Okay, so we're looking for all numbers that are greater than 7 and less than 4. So all numbers that are greater than 7 and less than 4. So if you draw a number line here, here's 4, here's 7. So we're looking for all the numbers that happen to be over here, so greater than 7 and less than 4 over here. So the problem is that if you pick a number that's over here, there's no way it can be over here, right? And vice versa. If you pick a number over here, there's no way that it can be over here. So there are literally no numbers that would satisfy this condition. There is no real number that if you plugged it in, either into this equation or into the original equation, would make it true. And if you don't believe me, you're more than welcome to try, but you can try all you want. You won't be able to find anything. So what we'll do here is, for these, a lot of times when they ask, hey, graph it, you're just going to say, hey, no solutions. If they ask you for the interval notation, sometimes we'll put the empty set. This right here is called the empty set. It is the set which contains nothing. Okay, so that can be your answer for interval notation. You could also say no solutions for interval notation. You can put the empty set. For set notation, you should put the empty set. because that's literally used for set notation. Want to look at, I think, 3 more examples here, and then you'll be done here. Okay, so what about this? So what if I had something like x is greater than or equal to 6, or x is less than or equal to 4. So we're used to working with the and, but now we're going to talk about what happens if we work with an or. So let's go ahead and draw this out on the number line. So if we have a number line and we put 4 and 6 on here, so I'm looking for all numbers that happen to be greater than or equal to 6. So I'm just going to shade that in on its own. That's that. Or numbers that happen to be less than or equal to 4. So that would be this way. And if you think about it, this, what I've drawn right here, is actually the answer if we were asked to graph this. Because what we're doing is we're showing all numbers, all possible numbers that are either greater than or equal to 6 or less than or equal to 4. So for instance, if I picked, let's say, 8 over here, would 8 fall into the category of either being greater than or equal to 6? Yup. Is it less than or equal to 4? No, it's not. Here's the thing. We don't need both of these things to be true. We just need to satisfy one of these conditions. So 8 over here satisfies needing to be greater than or equal to 6. It doesn't satisfy needing to be less than or equal to 4, but that's fine because we only need to satisfy one condition. Okay. What about 5? If you pick 5, okay, so 5 is right here in the middle. Is 5 greater than or equal to 6? Nope. Is it less than or equal to 4? Nope. So 5 should not be a part of our solution set. And if you look, it's not, right? We're not shading in between 4 and 6. And just so you can visualize this, how about if we pick something less than 4? How about 3? Okay, is 3 greater than or equal to 6? No. Is it less than or equal to 4? Yes. So 3 should be in our solution set. So this is why we shade everything above 6 and below 4. Next thing we want to talk about is interval notation. On this one, what we're going to do is we're going to say, okay, everything from negative infinity all the way up until 4, and we're going to break, and then we'll pick back up again at 6 and go to positive infinity. So the way that we do that is we say, all right, going all the way back to negative infinity up until 4, that's fine. We're going to include 4, so we put a bracket instead of a parentheses. And then here's a little thing we use. This is new to you probably. It is a union symbol. It looks like a U. So what all this does is it's saying, hey, you can either be here or here. The union is just basically a symbol for the word or. And then what we're going to do is we're going to pick back up at 6 with a bracket because we're going to include 6. And then we're going to go all the way until infinity. And we always put a parenthesis on infinity. So that's interval notation. And then set notation here for this one would be the set of all numbers x and the real numbers such that x is less than or equal to 4 or x is greater than or equal to 6. So we'll basically just kind of rewrite what we had up there. But that right there is set notation. Okay, so let's look at another example here. What if we had something like x is greater than or equal to 3 or x is greater than or equal to 5? Let's go ahead and draw a number line here. Here's 3, here's 5. And so we're trying to find all numbers that are either greater than or equal to 3, so I'll shade that first, or greater than or equal to 5. So anything that satisfies either one of these or both of them would work. So what I'm going to do is I'm going to shade some areas here. I'm going to shade a green area and an orange area and a blue area. And I'm going to ask, if something happens to fall in the green area, is it part of our solution set? Is it part of the numbers that would work here? So let's pick a number in the green area, like let's say 1. Okay, so 1's over in the green area. 1 happens to fall about, I don't know, right there. Is 1 greater than or equal to 3? No. Or is it greater than or equal to 5? No. So 1 should not be in our solution set. I'm going to say actually anything in the green area is not in our solution set. What about stuff in the orange area? So what if I pick like 4? 4 happens to fall about right there. Is 4 greater than or equal to 3? Yep. Or is it greater than or equal to 5? It is not that. Now, here's the thing. 4 happens to satisfy this condition, but it doesn't satisfy this one. The nice thing is, it only needs to satisfy one of the conditions. So 4 is good. So anything in the orange area is actually good to go. What about the blue area? Well, the blue area, anything in the blue area, like let's say 6, for example, would actually satisfy both conditions. It's both greater than or equal to 3 and greater than or equal to 5, which is awesome. It really only needed to satisfy one condition. So that's good to go. So what would our answer be then if we were going to actually fill out a number line for this? Here's what our actual answer would look like. We would put a 3 here. You actually don't even need the 5. I mean, I know the 5 is part of the problem, but remember, anything greater than or equal to 3 technically works here. So that's what I would shade for my number line there. Let's talk about our interval notation and set notation. I'm going to zoom out just a little bit here. So our interval notation here, so interval notation. In this case, we would take anything greater than or equal to 3. So we would go bracket 3, comma, infinity, parenthesis. That's our interval notation. Our set notation is going to be the set of all numbers x in the reals such that x is greater than or equal to 3, because that satisfies everything. We don't even need to mention the 5, because really all you have to be is greater than 3. Okay, and let's look at one last example here, and that is x is greater than or equal to 2, or x is less than or equal to 7. So a lot of times what I'll do on these is I will visually kind of draw it first, and then if I have to redraw, like I'll get a piece of scrap paper or something, and then I'll draw the actual answer on the number line, especially if I only have one number line on a worksheet or something. Okay, so we need to be greater than or equal to 2. So let's shade that in, greater than or equal to 2. That would be this guy. Or we can be less than or equal to 7. So that's going to be here going this way. And so let's do our zones again. I kind of like to think about this in zones. So here's the green zone, here's the orange zone, here's the blue zone. So how do we feel about things in the green zone? What if I pick a number over here? Oh, not the highlighter, the pen. What if I pick a number right here? So like 1, for example. Is 1 greater than or equal to 2? I'm going to say no. Is it less than or equal to 7? Yes. So 1 satisfies this condition right here. So 1 is good to go. In fact, anything in this green area is good to go. How about the orange area? What if I picked, I don't know, how about 4? So something like right in the middle here. If we pick 4, does 4 satisfy being greater than or equal to 2? Yes. Does it satisfy being less than or equal to 7? Yes. It actually satisfies both of them. So 4 is good to go. In fact, anything in the orange zone would also be good to go. What about in the blue zone? What if I pick something like 8? So 8, is 8 greater than or equal to 2? Yep. Is it less than or equal to 7? Nope. But the nice thing is we only had to satisfy one condition, and we satisfied this condition. So 8, and in fact, anything in the blue area would work. So the blue area is also good to go. Now, what's weird about this is that all 3 of our areas here, like the green, which goes forever, the orange, which is just right here, and the blue, which goes forever this way, anything in any one of those areas works. And the reason for that is because you have an overlap, right? So this one starts down here and goes up. This one starts down here and goes down. So there's nowhere on the number line that isn't covered by one of these 2 inequalities, okay? So your answer here, if you were actually going to draw this on a number line, I'm going to redraw the number line here. I'm not even going to put numbers on it. I'm just going to shade the entire thing. And just put some arrows on it to indicate, hey, I've shaded the entire number line. Okay, so that's great. How about for interval notation? So interval notation. How do we say that? Well, how do we say all real numbers in interval notation? What would be the starting number at the bottom? Well, it would be negative infinity. And then what would be the ending number at the top? It would be positive infinity. So that's interval notation. How about set notation? For set notation, it depends on who you talk to. Some people will put, the set of all numbers x such that x is in the real numbers, which is basically just saying all real numbers. Some people might say something to the effect of, they might just put all real numbers, which is just the bold-faced R, which is basically just an R with an extra vertical line going through it. Some people will literally write all real numbers. Okay? And that's about it.